Cosmic distances and the architecture of space, understanding our place in a universe beyond comprehension. When we talk about how big the universe really is, we're entering into a realm that's almost impossible for our minds to truly grasp. And yet here we are, these tiny biological machines on a small rocky planet, attempting to measure something so vast that the numbers themselves become meaningless after a while. I often think about this when lying in bed at night, looking up through the window at whatever stars are visible through the light pollution. Those pinpricks of light represent distances so enormous that even light itself, traveling at the fastest speed possible in our universe, takes years, decades, centuries to reach us. And that's just our immediate cosmic neighborhood. Let's start with something we can almost wrap our heads around. The distance from Earth to our Sun is about 93 million miles, or 150 million kilometers. We call this distance an astronomical unit, or AU. It's a handy measuring stick for our solar system. Neptune, the outermost major planet, orbits at about 30 AU from the Sun. So if you imagine the Earth-Sun distance and then multiply it by 30, Neptune is 30 times further out. Already we're talking about distances that would take our fastest spacecraft decades to traverse. Yet as vast as these distances seem, they're utterly negligible on cosmic scales. They're like measuring the distance from one room to another in a house the size of a continent. The Kuiper Belt, that region of icy bodies beyond Neptune's orbit, extends to perhaps 50 AU. The Oort cloud, the theoretical spherical shell of comets surrounding our solar system, might extend to 100,000 AU or more. At these distances, the Sun becomes just another star, indistinguishable from thousands of others. Our entire solar system, this collection of planets and moons and asteroids that seems so vast to us, it's like a grain of sand in a desert when we consider our galaxy. The nearest star to our Sun, Proxima Centauri, is about 4.24 light-years away. Now, a light year is not a measure of time, but of distance. It's the distance that light travels in 1 year. At 186,000 miles per second, light covers about 5.88 trillion miles in a year. So Proxima Centauri is roughly 25 trillion miles away. Think about that for a moment. If you could somehow travel at the speed of light, which you cannot according to Einstein's fundamental laws, it would still take you over 4 years just to reach our nearest stellar neighbor. And that's nothing compared to the scale of our galaxy. The Milky Way galaxy, our cosmic home, contains somewhere between 100 and 400 billion stars. The estimates vary depending on which study you consult, but let's say 200 billion for the sake of argument. Each of those stars is potentially like our Sun, possibly with its own family of planets. The galaxy itself is about 100,000 light-years across. So if you started a journey across the galaxy at the speed of light when the first modern humans were just beginning to create cave paintings in Europe and Southeast Asia, you'd be arriving at the far edge right about now. Imagine that timeline. The entire recorded history of human civilization, the rise and fall of empires, the development of technology, all of it would have occurred during just one edge-crossing journey across a single galaxy at the speed of light. And here's something that always gives me pause when I contemplate it. We're not even in the center of our galaxy. We're out in what astronomers call the Orion Arm, a minor spiral arm about 26,000 light-years from the galactic center. We're in the suburbs, you might say. We're in a backwater region of the galaxy, far from the cosmic action happening near the supermassive black hole at the galactic center. The galactic center, with its supermassive black hole called Sagittarius A star, is so far away that the light reaching us from there began its journey when our ancestors were just learning to make stone tools. We see the galactic center not as it is now, but as it was 26,000 years ago. But the Milky Way, Our entire galaxy, with its 200 billion stars, is just one galaxy among, well, we're not entirely sure how many. Recent estimates suggest there might be 2 trillion galaxies in the observable universe. 2 trillion, each one potentially containing hundreds of billions of stars. The Andromeda Galaxy, our nearest large galactic neighbor, is about 2.5 million light-years away. It's actually heading towards us, and in about 4.5 billion years, it will collide with the Milky Way in what will be a cosmic catastrophe on unimaginable scales. But don't worry about that collision. The Sun will have already evolved into a red giant by then, making Earth uninhabitable anyway. It's funny how we plan for retirement when cosmic events make such long-term thinking seem almost quaint. When we look at Andromeda through telescopes, we're seeing it as it was 2.5 million years ago. The light that's hitting our detectors tonight left that galaxy when our ancestors were just learning to walk upright consistently. Every photon that enters your eye when you look at that smudge of light in the constellation Andromeda has been traveling through space for longer than our species has existed. And Andromeda, despite being our nearest major galaxy, is still within what astronomers call our local group. This is a gravitationally bound collection of about 80 galaxies, most of them small dwarf galaxies orbiting either the Milky Way or Andromeda. The entire local group spans about 10 million light-years across. But even our local group, this collection of 80 galaxies, is just a tiny part of something much larger. The local group is embedded within the Virgo supercluster, which contains about 1,300 galaxies spread across approximately 110 million light-years. Within this supercluster, there are thousands of galaxies, each containing billions or trillions of stars. And we're discovering that even superclusters are organized into larger structures, cosmic webs of matter separated by enormous voids. The observable universe, that spherical region of space from which light has had time to reach us since the Big Bang, has a radius of about 46.5 billion light-years. Now you might think, wait, if the universe is only 13.8 billion years old, how can we see things that are 46 billion light-years away? And that's a beautiful question that gets to the heart of cosmic expansion. You see, space itself has been expanding since the Big Bang. So while light from distant galaxies has been traveling towards us for billions of years, those galaxies have been moving away from us the entire time due to the expansion of space. It's like imagine you're on a moving walkway at an airport, but instead of the walkway moving you forward, it's stretching, making the distance between you and your destination longer even as you walk toward it. This expansion means that the most distant galaxies we can observe are actually much further away than 13.8 billion light-years. The light we're seeing from them shows us what they looked like when the universe was young, but they've since moved to distances of nearly 47 billion light-years due to cosmic expansion. And here's something that might keep you awake if you think about it too much, or help you sleep if you find it as mesmerizingly vast as I do. The observable universe might not be the entire universe. In fact, most cosmologists believe the actual universe extends far beyond what we can observe. It might be infinite. Imagine that. An infinite expanse of space containing an infinite number of galaxies, stars, and possibly an infinite number of worlds like our own. The cosmic microwave background, that faint afterglow of the Big Bang that permeates all of space, gives us a baby picture of the universe when it was only 330,000 years old. Before that, the universe was so hot and dense that atoms couldn't form and space was opaque to light. This radiation has been stretched by cosmic expansion from visible light to microwave frequencies, and it carries with it tiny temperature fluctuations that would eventually grow into the large-scale structure we see today. When I think about these scales, when I really try to internalize the vastness we're discussing, I find myself wondering about our place in it all. We're made of atoms forged in the cores of stars that lived and died billions of years ago. The carbon in our bodies, the oxygen we breathe, the iron in our blood, all of it was created through nuclear fusion in stellar cores or during the explosive deaths of massive stars. We are quite literally made of star stuff, as Carl Sagan so poetically put it. And now, through some remarkable quirk of cosmic evolution, these atoms have arranged themselves into brains capable of contemplating their own cosmic origins, with the universe becoming aware of itself. The numbers become almost poetry after a while. 1 billion is 1,000 million. 1 trillion is 1,000 billion. The number of stars in the observable universe has been estimated at around 10 to the 24th power. That's a 1 followed by 24 zeros, more than all the grains of sand on all the beaches.
The numbers become almost poetry after a while. 1 billion is 1,000 million. 1 trillion is 1,000 billion. The number of stars in the observable universe has been estimated at around 10 to the 24th power. That's a 1 followed by 24 zeros, more than all the grains of sand on all the beaches of Earth. And each star, each one of those distant suns, represents a potential story. Planets forming from cosmic dust, atmospheres evolving. Perhaps somewhere among those countless worlds, other forms of life looking up at their night sky and wondering just as we do about the immensity of it all. The James Webb Space Telescope has recently been showing us galaxies that formed when the universe was less than 400 million years old. These ancient galaxies appear redshifted due to cosmic expansion, their light stretched to infrared wavelengths during its billions of years of travel to reach us. In a sense, we're looking back in time, seeing the universe as it was when it was just a child. Some of these early galaxies are surprisingly large and well-formed, challenging our understanding of how quickly structure could have assembled in the early universe. It's as if we expected to see cosmic toddlers, but instead found, well, cosmic teenagers already showing signs of mature development. The expansion of space itself is accelerating, driven by something we call dark energy. This mysterious force, which makes up about 68% of the universe, is causing distant galaxies to recede from us at ever-increasing speeds. Eventually, in the far future, galaxies beyond our local group will disappear beyond the cosmic horizon, their light redshifted to wavelengths so long that they become undetectable. Imagine that future universe, where astronomers in the Milky Way would see only the stars of our own galaxy, and perhaps Andromeda, with no evidence that billions of other galaxies ever existed. They might conclude they lived in a small, static universe, never knowing about the vast cosmic web of galaxies that once filled the sky. Dark matter, making up about 27% of the universe, provides the gravitational scaffolding on which galaxies and galaxy clusters form. We can't see it directly, but we can observe its gravitational effects. It's like trying to understand the architecture of an invisible building by watching how people move through its corridors and stairways. The remaining 5% of the universe is ordinary matter, the stuff we're made of, the stuff we can see and touch and measure directly. We are a tiny fraction of a tiny fraction of what the universe contains. The largest known structure in the universe is the Hercules Corona Borealis Great Wall, a collection of galaxy clusters stretching across about 10 billion light-years. It's so large that light takes 17 times the age of the universe just to cross from one end to another. These cosmic walls and filaments, separated by vast voids, form what scientists call the cosmic web, a foam-like structure that represents the largest-scale organization of matter in the universe. In these voids, these empty regions between galaxy clusters, space is nearly empty. The density of matter is less than 1 atom per cubic meter. If you could somehow stand in the middle of one of these cosmic voids, the nearest galaxy might be tens of millions of light years away in any direction. The night sky would be almost completely black, with only the faintest smudges of light from the most distant galaxy clusters. But even these vast empty regions aren't truly empty. They contain dark matter, dark energy, and the occasional wandering galaxy. They're threaded with invisible filaments of gas that will, over cosmic time, feed the formation of new galaxies. When we measure cosmic distances, we use a series of overlapping techniques called the cosmic distance ladder. For nearby stars, we can use parallax, the apparent shift in a star's position as Earth orbits the Sun. For more distant objects, we rely on standard candles like Cepheid variable stars or Type A supernovae, objects whose intrinsic brightness we understand, allowing us to calculate their distance from their apparent brightness. Each rung of this distance ladder extends our reach further into space and further back in time. The Hubble constant, which measures the rate of cosmic expansion, has been determined through these methods to be about 70 kilometers per second per megaparsec. This means that for every 3.26 million light-years of distance, space is expanding at an additional 70 kilometers per second. The cosmic microwave background, this ancient light that fills all of space, is remarkably uniform in temperature, varying by only tiny fractions of a degree across the entire sky. And yet those tiny variations, those quantum fluctuations from the earliest moments after the Big Bang, they're the seeds from which all cosmic structure grew. Think about that for a moment. The galaxy cluster where we sit right now, the Virgo supercluster with its thousands of galaxies, it all began as a region of space that was perhaps 1 part in 100,000 denser than average when the universe was less than 400,000 years old. Gravity amplified that tiny difference over billions of years, drawing matter together, igniting the first stars, forming the first galaxies. The largest structures we observe today grew from the tiniest quantum fluctuations in the primordial universe. The redshift-distance relationship, it's perhaps the most profound observational discovery in the history of cosmology. When Edwin Hubble first noticed that more distant galaxies appeared systematically redder than nearby ones, he was observing the expansion of space itself, made manifest in the spectrum of starlight. Redshift occurs because cosmic expansion stretches the wavelengths of light as photons travel through space. A photon that starts its journey as blue light might arrive at our telescopes as red light, or even infrared radiation, depending on how far it has traveled and how much the universe has expanded during its journey. The greater the redshift, the more distant the galaxy, and the further back in time we're seeing it. This stretching of light, it's happening to every photon that travels through space, including the light you're seeing right now. But on the scales of everyday life, even on the scale of our solar system, cosmic expansion is completely negligible compared to other forces. It's only on scales of hundreds of millions of light years that cosmic expansion begins to dominate over gravity and other influences. The habitable zone around stars, that region where liquid water could exist on a planetary surface, exists within the context of these cosmic scales. For our Sun, it extends roughly from Venus's orbit to somewhat beyond Mars. But the habitable zone isn't static. As stars age and brighten, their habitable zones move outward. In about 1 billion years, Earth might be too hot for liquid water, while Mars might become more hospitable. The concept of habitability, it's fundamentally tied to these cosmic distance scales and the ways that matter and energy distribute themselves across space. The local supercluster, our cosmic neighborhood, contains about 1,300 galaxies and spans roughly 110 million light-years. But even this vast structure is just a small part of something even larger, the Laniakea supercluster, discovered only in 2014 through detailed mapping of galaxy motions. Laniakea is a Hawaiian word meaning immense heaven, and it's an apt description. This supercluster contains about 100,000 galaxies and spans 520 million light-years. All the galaxies in Laniakea are flowing toward a region called the Great Attractor, a gravitational anomaly hidden behind the disk of our own galaxy. The discovery of Laniakea required mapping the peculiar velocities of thousands of galaxies, that is, their motion relative to the overall cosmic expansion. Most galaxies are moving away from us due to the expansion of space, but they also have additional motions caused by the gravitational pull of nearby massive structures. By mapping these motions, astronomers can trace the underlying distribution of matter and identify the boundaries of cosmic structures. What they found was humbling. The Milky Way, Andromeda, and all the galaxies we can see with the naked eye were just tiny components of this vast river of galaxies flowing through space. We're not just orbiting the sun, and the sun isn't just orbiting the galactic center. We're all participating in motions on scales of hundreds of millions of light-years. The cosmic web
that emerges from these observations looks remarkably organic. Galaxies are strung along filaments, like cells in living tissue, separated by vast voids that contain almost nothing. The filaments themselves intersect at nodes where galaxy clusters form, the densest concentrations of matter in the universe. The Coma cluster, about 320 million light-years away, contains over 1,000 galaxies bound together by gravity. The space between these galaxies is filled with hot gas at temperatures of millions of degrees, so hot that it glows in X-rays. This intracluster medium contains more mass than all the galaxies combined. When galaxy clusters collide, and they do collide over cosmic time, the results are spectacular. The Bullet cluster is a famous example of two galaxy clusters that passed through each other about 150 million years ago. The hot gas from each cluster collided and was stripped away, but the galaxies themselves and their dark matter halos passed through relatively unaffected. This separation of ordinary matter from dark matter provides some of the strongest evidence that dark matter actually exists as a distinct component of the universe. The most distant galaxies we can observe formed when the universe was less than 5% of its current age. These early galaxies appear smaller and more chaotic than modern galaxies, as if we're seeing cosmic evolution in action. Many of them are undergoing intense bursts of star formation, creating new stars at rates hundreds of times faster than what we see in today's galaxies. The James Webb Space Telescope has revolutionized our view of these early galaxies. Its infrared vision can peer through cosmic dust and detect the stretched light from the most distant objects. Some of the galaxies it has found are surprisingly massive and well organized for their age, suggesting that galaxy formation proceeded more rapidly in the early universe than we previously thought. One of the most profound implications of cosmic scale is temporal. When we look at distant galaxies, we're not just seeing across space, we're looking back in time. The further we look, the younger the universe appears. At the edge of the observable universe, we're seeing the cosmic microwave background, light from when the universe was only 380,000 years old and atoms were first forming. This means that our observable universe is not a snapshot of space at a single moment in time. It's more like a light cone with the present moment at its tip and the Big Bang at its base. Every photon that reaches our telescopes carries information from a different epoch in cosmic history. We're not just astronomers, we're cosmic archaeologists, piecing together the history of the universe from the ancient light that reaches us across billions of years. The redshift of distant galaxies tells us not just how far away they are, but also when we're seeing them. A galaxy with a redshift of z equals 1 appears as it was when the universe was about half its current age. A galaxy with z equals 10 shows us the universe when it was less than 500 million years old. The highest redshift galaxies we've detected have z values around 13, showing us the universe when it was barely 400 million years old. At these extreme distances and look-back times, we're seeing the universe during the epoch of reionization, when the first stars and galaxies were energetic enough to ionize the hydrogen gas that filled intergalactic space. Before this epoch, space was dark and filled with neutral hydrogen. After reionization, space became transparent to ultraviolet light, allowing us to see the first galaxies. The scale of cosmic time, it's almost as mind-bending as the scale of cosmic space. If human civilization is a few seconds on the cosmic calendar, then individual human lifetimes are measured in milliseconds. The rise and fall of entire empires, the extinction and evolution of species, the formation and erosion of mountain ranges, all of these occur in what amounts to the blink of an eye on cosmic timescales. And yet, here we are, these brief arrangements of atoms, contemplating structures that span billions of light years and events that occurred billions of years ago. Through science, through careful observation and mathematical analysis, we've extended our reach far beyond the tiny corner of space and time that we actually inhabit. The universe is under no obligation to make sense to us, and yet somehow it does. The same physical laws that govern the fall of an apple on Earth also describe the orbits of planets around distant stars and the expansion of space itself. The mathematical language we've developed to describe phenomena in our laboratories also applies to black holes and neutron stars and the cosmic microwave background. This universality of physical law across cosmic scales of space and time is one of the most remarkable discoveries in the history of science. It suggests that our small corner of the universe is not special, that the physics we can study here applies everywhere and every when. The concept of cosmic horizons, it's something that really makes you pause and think about the limits of knowledge itself. We have the observable universe, that sphere of space from which light has had time to reach us since the Big Bang. But there's also the particle horizon, the distance to the most distant object whose light could theoretically reach us, and the event horizon, beyond which we will never receive signals due to the accelerating expansion of space. These horizons are moving boundaries. Every second, light from slightly more distant objects crosses into our observable sphere. We're constantly receiving the first light from regions of space we've never seen before. And yet simultaneously, the acceleration of cosmic expansion means that galaxies at the edge of our current observable universe are moving away from us so quickly that we'll eventually lose contact with them forever. It's a strange thought. There are galaxies shining right now, filled with billions of stars, that we will never see because their light will never have enough time to reach us before cosmic expansion carries them beyond our cosmic horizon. There could be civilizations out there right now, looking up at their night sky, completely unaware of our existence simply because we exist in causally disconnected regions of space.
The cosmic light horizon, it's currently about 46.5 billion light-years away, but it's not static. It's growing at the speed of light, about 1 light-year per year. This means that every year we can potentially observe events that occurred 1 light-year away from us. The universe is gradually revealing more of itself to us, one layer at a time, like an onion slowly peeling itself. The regions of space beyond our current horizon aren't fundamentally different from the space we can observe. The laws of physics should be the same. The distribution of matter should follow similar patterns. Galaxies should form and evolve in much the same way. We're seeing a representative sample of a much larger, possibly infinite cosmos. The homogeneity principle in cosmology suggests that on the largest scales, the universe looks essentially the same in all directions and at all locations. This doesn't mean that every region of space contains identical galaxies, rather that the statistical properties of the universe should be similar everywhere. The average density of matter, the typical sizes of structures, the rate of star formation should be similar in all regions. If we could somehow travel to a galaxy 10 billion light-years away and look back toward the Milky Way, we would see a cosmic web of filaments and voids statistically indistinguishable from what we observe from our current vantage point. The specific arrangement of galaxies would be different, of course, but the overall patterns would be recognizably similar. This uniformity on cosmic scales is actually quite surprising when you think about it. Regions of space, separated by billions of light-years, have never been in causal contact. They've never had enough time since the Big Bang for light signals to travel between them. And yet they have almost identical temperatures and densities. It's like finding that two people who have never met are wearing identical outfits. Cosmic inflation provides an explanation for this uniformity. If all the regions we can observe were once in close causal contact before undergoing exponential expansion, then they would naturally have similar properties. It's as if they're all fragments of the same original region of space, stretched apart by inflation, but retaining the memory of their common origin. The scale factor of the universe, it's a measure of how much space has expanded since any given time in the past. When we say the universe has doubled,
Cosmic inflation provides an explanation for this uniformity. If all the regions we can observe were once in close causal contact before undergoing exponential expansion, then they would naturally have similar properties. It's as if they're all fragments of the same original region of space, stretched apart by inflation, but retaining the memory of their common origin. The scale factor of the universe, it's a measure of how much space has expanded since any given time in the past. When we say the universe has doubled in size since some earlier epoch, we mean that the scale factor has doubled. All distances between distant objects have stretched by the same proportion. It's not that objects are moving through space, but rather that space itself is expanding, carrying objects along with it. This expansion affects different scales differently. Gravitationally bound systems like galaxies, star systems, and even atoms are not expanding with the universe. The electromagnetic forces holding atoms together, the gravitational forces binding stars in galaxies, these are strong enough to resist cosmic expansion on these smaller scales. It's only on scales larger than galaxy clusters that cosmic expansion dominates over local gravitational attraction. So when cosmologists say that space is expanding, they don't mean that your room is getting bigger or that the Earth is moving away from the Sun. They mean that the typical distance between galaxy clusters is increasing over time. The Milky Way and Andromeda are actually approaching each other because their mutual gravitational attraction is stronger than the local expansion of space.
But distant galaxy clusters that are not gravitationally bound to us are indeed receding due to cosmic expansion. The mathematics of cosmic expansion leads to some fascinating implications for the far future. If dark energy continues to drive accelerating expansion, and we have no reason to think it won't, then the universe will enter a phase called the Big Rip. In this scenario, the expansion becomes so rapid that it eventually overcomes all forces, tearing apart galaxy clusters, then galaxies, then star systems, then planets, then atoms themselves. But this is far in the future, so far that it makes the current age of the universe seem like an instant. We're talking about timescales of trillions upon trillions of years. The last stars will have died, black holes will have evaporated through Hawking radiation, and the universe will have become a cold, empty expanse before the Big Rip becomes relevant. Long before that, though, the universe will enter what cosmologists call the degenerate era. This is when the last ordinary stars will have exhausted their nuclear fuel and died, leaving behind white dwarfs, neutron stars, and black holes. The universe will be lit only by the occasional flare when a brown dwarf or a white dwarf accretes matter, or by the brief flash when two dead stars collide. Even these remnants will not last forever. Protons themselves may be unstable with half-lives of perhaps 10 to the 34th power years. If so, then even the white dwarfs and neutron stars will eventually decay into elementary particles and radiation. Only black holes will remain, slowly evaporating through Hawking radiation until they too disappear in flashes of gamma rays. The final era in this cosmic timeline is called the Dark Era, when space is filled with nothing but elementary particles, photons, and the occasional positronium atom, an exotic atom consisting of an electron and a positron orbiting each other before annihilating. The temperature of space will approach absolute zero, and the entropy of the universe will approach its maximum value. But even in this far future, quantum mechanics suggests that random fluctuations in the vacuum might occasionally create temporary structures, virtual particles popping in and out of existence, perhaps even the spontaneous formation of complex systems through sheer chance over astronomical periods of time. It's a humbling thought that our current universe, with its galaxies and stars and planets, with its complexity and beauty and life, is just a brief, flickering moment in a cosmic story that will play out over timescales that dwarf the current age of the universe by factors of trillions upon trillions of years. And yet, here we are in this brief epoch, when stars are shining and planets are orbiting, and life has emerged from cosmic dust to contemplate its own origins. We exist at a special time in cosmic history, after the universe has had enough time to create heavy elements and form complex structures, but before expansion and entropy have rendered everything cold and lifeless.